Okay, so we're dealing with scientific notations, and scientific notations is really an easier way to work with really large or really small numbers. In both of these examples, 0 point and a whole lot of 0.56 seconds and 9034 and a whole lot of 0 kilograms. These are two measurements that are very small and also very large. So in an effort to make it more efficient and more effective when we're dealing with values and measurements, we want to put them into scientific notations. So essentially what this PowerPoint is really trying to do is to get you to work with scientific notations and doing basic mathematics. So scientific notations is basically expressing a really large or really small number as a power of 10. So the numerical part, which is the base number, designated by this in here as m. The m is the base number, and it has to be between 1 and 9.99999, or pretty close to 10. It should be basically a single digit number, a single digit whole number with a decimal value. And it's multiplied by a whole number power of 10, where 1 is greater. Well, 1 has to be, basically m has to be between 1 and 10. N is an integer, and what integer means is a whole number. It could be a positive or negative value. So when you have a number to be converted into scientific notation, you first, whether it's a small number or a large number, you have to move the decimal point of that value to make the base number m between 1 and 9.99999, so on and so forth. And based upon how many times the decimal point was moved and also in which direction, it's going to affect the power n of the power of 10 accordingly. So if the decimal was moved towards the right, basically making a really small number into a whole number, the power n will be negative. If the decimal is moved to the left, from the right to the left, making a large number into a smaller value for the base number, the n power will be positive. So let's see how this works out. If I were to look at this value here, 3,005,000 kilograms right over here, then to change that value into a scientific notation, the decimal point is going to be at the far right, closest to basically to the right of the last zero. And we're going to be moving this decimal point 1, 2, 3, 4, 5, 6 times. So that is essentially the n power. So our answer will be 3.005 times 10 to the 6th. The reason why it's times 10 to the 6th is because we moved the decimal point to the left 6 times. Now, if we're working with a really small number, and so we have a decimal point here. This decimal point will then be moved to the right 10 times. So our number for our scientific notation, the base number will be 4.2 because that base number must be between 1 and 9.9999, so on and so forth. So since we moved the decimal point once, twice, 3 times, 4, 5, 6, 7, 8, 9, 10 times, the answer is now going to be 4.2 times 10 to negative 10th millisecond. So it's a pretty small number. So having a scientific notation makes it easier to work with. Now, if we have a scientific notation, we want to convert it into a number. We just got to do the opposite. So you will move the decimal point from your base number m the same number of times as the power n. So if the n power is negative, you'll move the decimal point to the left. If the n power is positive, move the decimal to the right. Negative n power means that the number is really small. A positive n power means the value for that measurement is really large. So here we have 4 examples for you to kind of work through. The answers are given to you. And so you have a small number. You move the decimal point to the right, making the integer for the power to be negative since we're working for a small number. And we're moving this decimal point a total of 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Base number has to be between 1 and 9.99999. So our answer is 9 times 10 to negative 10th seconds. Same thing goes on for number 6. Your decimal point is not shown anywhere on this number. So we will have to say that the decimal point is at the very right. And we're moving this decimal point to the left because we have to get the base number between 1 and 9.99. So we're moving this a total of 7 times. 1, 2, 3, 4, 5, 6, 7. So we have 3.5 times 10 to the 7th kilometers. Now, 7 and 8 is basically something that we are going to work with to get the scientific notation into a numerical value. So since the exponent is positive 5, we know that this value is actually much larger than 8.6. So we're going to move the decimal point to the right. A total of 5 times, giving us an answer of 860,000, or otherwise known as 160,000 meters. And since the number 8, we have a negative 8 as the exponent. We know that the value for this measurement is quite small. And we're going to be moving the decimal point 8 times to the left, giving us 0.7062 grams. So it's a pretty small number. Now, when we're doing basic mathematics, dealing with scientific notations, there are certain rules. So just like in, I guess, Algebra 1, we got to make sure that all our powers are the same before we can do any mathematical operations. So in order for you to do that, you'll add or subtract the base number after you make sure the powers are the same. So then once that has happened, you will then look at the units, powers, then do the mathematical operation. So it's kind of confusing now, but I think with an example or two, you might kind of get it. So you might want to take out a sheet of paper and a pencil and see if you can do it. Now, of course, you should be taking notes now, so the paper and pencil should be already out. So here we have 4 examples of adding or subtracting scientific notations, and the math is not too bad. So the first bullet point, 4.67 times 10 to the 4th grams plus 3.4 times 10 to the 4th grams. You make sure that the exponents are the same, and you got to make sure that units are the same. If the units are not the same, you have to change the units first. After units are the same, moving the decimal or changing the exponents, just like what we did last week for the metrics quiz, do that first, and then look at the exponents. Make sure the exponents are the same. Once you change the exponents to be the same, then you're able to do the math. Okay? So since the units and the exponents are the same, we can very easily just add the base numbers, 4.67 plus 3.4. And that comes out to be 8.07 as the base number. And because this is adding or subtracting, all we need to do is just keep the power the same and keep the unit the same. So it comes out to be 8.07 times 10 to the 4th grams. Now the second example is the same thing. The units are the same, exponential power is the same because it's 10 to the 3rd meters for both parts of this equation. 5.74 times 10 to the 3rd meters plus 6.55 times 10 to the 3rd meters. So when you add the base numbers together, it comes out to be 12.29. Keeping the units the same and keeping the exponents the same, we have 12.29 times 10 to the 3rd meters. Now here's the problem. The problem is we need to figure out a way to keep this answer in the correct format with a scientific notation. So we have 12.29 as the base number, and we got to keep the base number between 1 and 9.99. So we got to move the decimal point to the left 1 time, making the exponents larger by 1, since we increased the power by 1. So 1.229 times 10 to the 4th meters. And that's for the second bullet point. And for the third bullet, we have 8.5 times 10 to the 4th seconds plus 3.5 times 10 to the 3rd seconds. Units the same. Keep it the same. So we don't have to change anything. But because the exponents are the same, we got to change one of the 2 terms to match each other. So since 8.5 times 10 to the 4th seconds is the larger of the 2, I generally keep that by itself and don't do anything to it. and just change the 3.5 times 10 to the third to something times 10 to the fourth seconds. So how am I going to change 3.5 times 10 to the 4, well, 3.5 times 10 to the third seconds to something, some base number value times 10 to the fourth seconds? So you might have guessed already that you're just going to move the decimal point. And since we got to move the decimal point to change the number of the base value to something 10 to the fourth, we'll move the decimal point to the left by 1. So it becomes 0.35 times 10 to the fourth seconds. So we can add the base number, 8.5, plus 0.35, and we get 8.85. Keeping the units the same and the exponents the same, it'll be 8.85 times 10 to the fourth seconds. Now the fourth bullet is a little bit more challenging, seeing that the units are not the same and the exponents are not the same. So the first step is to change the units so they do become the same. So let's just say we look at the answer and we know that the answer is has to be measured in terms of a kilogram. A kilometer. So in that case, what we'll do is we're going to convert the meters to kilometers from the term 2.5 times 10 to the 8th meters. So since meters is 10 to the 0, kilometer is 10 to the third, we're going to change the exponents by a factor of 3, smaller, because kilometer is larger, meter is smaller, therefore the number in front of the kilometer must be smaller. So we're going to reduce the exponents by 3, since the difference between 10 to the 0 and 10 to the third is negative 3, subtract 3. So now we have 2.5 times 10 to the fifth kilometers plus, and since we changed it, the exponents and the units on the second term to be the same to the kilometers, so it'd be 2.5 times 10 to the fifth kilometers. So we have two terms that are that have the same units, and therefore we have 5.0 plus 2.5 plus 2.5 is 5.0. Keeping the units the same, keeping the exponents the same, we have the same. The answer is 5.0 times 10 to the fifth kilometers. So pause if you need to. Go ahead and do that if you need to in order for you to practice this. I know, and we'll be able to do some more in class. Now, when you're multiplying or dividing scientific notations, there are several steps. Essentially, I think it's easier than adding and subtracting, because when you're multiplying, we just multiply the base numbers and then we add the exponential power. Then we multiply the units together. When we're dividing, we divide the base numbers, then subtract the end powers, and then we divide the units. So make sure that the answer is in the correct scientific notations format, and that's pretty much it. So here are 4 more examples. If you have two terms, 3.0 times 10 to the fourth meters times 4.0 times 10 to the fifth meters, we very simply just multiply the base number. 3 times 4 gives us 12. And then what we'll do is we'll add the exponents. So it's times 10 to the 9th. Then we multiply the units, meters squared. By doing so, we have 12 times 10 to the 9th meters squared. Essentially, we just got to change it so that it's in the correct scientific notations format to 1.2 times 10 to the 10th meters squared. All right. Second bullet is the same thing, except when you're adding the exponents, negative 5 plus 6. Remember that is a negative value, so you got to subtract. So the answer comes out to 1.0 times 10 to the second meters cubed. And remember again, the reason why that's the answer is because we had to change the number, base number to the correct scientific notations format. When we're dividing, very simply, 9.0 divided by 2.0, we get 4.5. Write that down. Then we take the exponents and subtract the exponents. Times 10 to 8 minus 5 gives us 3, so times 10 to the third. Meters squared divided by meters. We divide the units. We treat them as a separate entity, so it's meters squared divided by meters, giving us only meters, because one of the meters from the meter squared cancels out. Same thing for the fourth bullet, and just work through that, and the answers are given to you, so you're able to check your answers. That's pretty much it for scientific notations. So if you have any questions, please ask on Tuesday, and definitely we'll try to do this a little bit more sequentially during class time.